So we are going to start with the mechanical design of the Articulight system. Our original design used interlocking connectors as the arm, but we found this to be too rigid. So we went with a continuum arm design using a spring, which allows for more fluid motion. If the light uses a standard 120 volt socket, the camera mount was modeled and 3D printed for a Raspberry Pi camera and connected via these copper tubes to make to the first segment to make both of these move as one unit. Each segment was modeled and 3D printed to act as a guide for the spring as well as wire guides for the system movement. The case was originally made from plexiglass, designed and made from plexiglass, but upon testing, during actuation, we found that the plexiglass tended to flex. So we redesigned for a sturdier structure. The case uses a double hinge in order to allow for easier access to the PCB and servos. These pulleys and servo mounts are both modeled and 3D printed, and the stands for the servo mounts are made from L brackets and copper to act as heat sinks.
For our circuit design, we wanted it to utilize 120 volts AC from the wall as well as power our 5 volt DC circuit board all within the same power source. 120 volt AC is going to get split into two. One goes straight into our 120 volt light while the other goes into our 5 volt circuit board. The circuit board goes into a step-down transformer where the input voltage goes from 120 volt VAC to 12 volt VAC output. 12 volt VAC splits into a single phase bridge rectifier which turns the AC signal into a DC signal. One half of the circuit is designed with the PNP transistor to carry the extra current since our voltage regulator has a maximum output of 1.5 amp and we needed 3 amps, and this will power the Jetson Nano and servo motor since it requires a higher current. The other half of the circuit goes into our microcontroller since it was designed for a lower current.
Here, we showcase the image collection program for generating a dataset. Written in Python, this script allows us to generate datasets to train the support vector machine for gesture detection. The program prompts the user to enter the name of the dataset and how many gestures they wish to train. Once this information is gathered, the program loops through the number of gestures and prompts for a label for each one. Then, a GUI is instated with buttons for the following actions: save image, save 600 images, save 100 images, next gesture, previous gesture, toggle trainer test, and exit. Save image saves a single image to the current gesture directory. Save 600 images and save 100 images save 600 and 100 frames in a row as an image for each frame. This allows the user to move and rotate their hand for the duration of those frames to get a robust dataset for each gesture. The next and previous gesture buttons let the user update the directory and therefore the gesture that the save image buttons save images to. When this button is clicked, the updated directory is printed to the console. Toggle trainer test lets the user signal whether the dataset is a training or testing dataset for the SVM model. After the image collection is complete and the exit button is pressed, the program renames each image from random strings and names them numerically counting from 0. A JSON file is generated that maps the label to each image, which is required for supervised learning models such as support vector machines.
To test the average computation time of our gesture tracking software, we created a control variable at the start of our while loop, which determines the amount of time it takes from the first line of the loop to the end of the loop and calculates an average time for that. This is bottlenecked by our frame rate, which is set to 8 frames per second in order to reduce lag. The data shows an average of 1.25 seconds, or 1/8 of a second, which aligns with the frame rate we implemented. The data is sent to the Atmega 325p to process the pixel location for actuation. The timing of the Atmega processing is approximately 1.1112 seconds, or just over 1/10 of a second of delay, bringing the total time, computation time, of around 0.225, or approximately 1/5 of a second. Next, I would like to demonstrate how we tested the servo actuation time. The Atmega was programmed to perform a 180-degree servo sweep in both the X and Y axis, forward and backwards, at 1 degree at a time. This was then sent to the servos for actuation with a 10 millisecond delay in between each movement. This was then followed by a random movement in both the X and Y axis to simulate the move to command. All of this data, the start and stop times, were printed to the serial monitor along with the timestamps, which was then compiled in Excel to determine the overall servo actuation time for both X and Y sweeps and the random movement. Okay, now we're going to demonstrate how we tested the accuracy of our move to function. So we mounted a laser pointer to the head of our robotic arm, where the light, in line with the light. I'd like to make an important distinction that notice the laser is centered on the frame of the camera, so it does not matter that it is not centered on the work surface. When we use the thumbs up command, it triggers the actuation to move to the thumb position. And from there, we can use a ruler to actually measure the distance between the light and the thumb. Okay, first we're going to go over all of the gestures we have our machine learning algorithm recognize. So we start with no hand, open palm, 3, thumbs up, and rock on. Next we're going to demonstrate the follow me gesture. This is activated with the rock on gesture, and it follows the pointer and trying to keep it in the center of the frame, the camera's frame. Then from there, just do the rock on again for 8 frames or 1 second, and it will turn it off. Okay, so the next gesture I'm going to demonstrate is the reset. This is done simply by holding a 3 for 8 frames or 1 second. Then once it captures that, it will reset to a default position that we had pre-programmed in. So our last gesture that we're going to demonstrate is the move to gesture, which is signified by a thumbs up. So if this project were to continue, some of the things that we would like to improve on is to refine our gesture recognition and to make it more robust and to include more gestures, to refine our follow me, or sorry, if this project were to continue, we would like to refine our gesture recognition to include more gestures, to add more functionality, and to definitely refine our servo movement with some controls, smooth out the movement, the overall actuation, and to adjust the move here command so that it can work in a horizontal position or more horizontal position, because currently it can only do a vertical movement. So we appreciate your time and consideration. We are Group 9, and this is the Articulight. Say goodbye, Articulight!